See, ionization is the amount of energy that is required, okay, to remove the loosely bounded electrons in the ground state of an isolated gaseous state atom. For example, this is an atom in gaseous state. So to remove this electron, how much amount of energy that we are using is what we call it as ionization. In case if you are removing the first electron, we call it as first ionization. If you are further releasing the second electron, we call it as second ionization. Generally, ionization energy keeps increasing as you start removing out every successive electron. So, what could be the reason? The reason is simple. When it is in a neutral form, the size of the atom would be relatively bigger. As it starts getting positive charge, the size of the atom will become smaller and smaller. So, removing an electron from a small sized atom or ion becomes very, very challenging. Okay. Second thing, ionization is an endothermic change. That means energy is required. It is usually measured in electron volts per atom or kilojoules per mole. What are the factors that influence the ionization? First factor is atomic size. If the size of the atom is bigger, ionization is smaller. That's what you will encounter almost in every group going down. That is from lithium towards cesium, you will see ionization increases or decreases. Fluorine towards iodine, ionization decreases. Second factor is effective nuclear charge. If the effective nuclear charge is higher, it becomes difficult to relate or difficult to release the electron or remove the electron from the outermost electron. If screening factor is more, screening factor relates to how much amount of inner electrons inner electrons are shielding the outermost electron. So the amount of this which they are shielding is what we call it as shielding factor or screening factor. So if that factor is also more, it is easy to remove the electron. Okay. Usually the electrons present in s orbital have a stronger screening than p orbital than d orbital, which is likely to say that if you have more number of s orbital electrons, the outermost electron is easy to remove. Okay. The next factor is n. If n factor, that is quantum number factor, increases, then ionization decreases. In short, if you're talking about the first shell, second shell, third shell, and fourth shell, so as you go towards the higher shells, the size of the atom is increasing. So naturally, ionization decreases. Next one is penetrating power. If it comes to SPDF, removing an electron from s orbital would be more challenging than p orbital, d orbital, and f orbital. Okay, this is ionization energy, how it varies for. When it comes to beryllium, for example, removing an electron from 2s orbital is more challenging than removing an electron from 2p in boron. That's the reason the first ionization of beryllium is greater than first ionization of boron. And this logic can be applied to the next elements also. That is, if you take the first ionization of magnesium, it is greater than first ionization of aluminum. The next factor is half-filled and full-filled stability. Nitrogen, for example, will have 3 unpaired electrons in degenerate orbitals. 2p has 3 set of orbitals, all of them have same energy. Orbitals which have same energy, we call them as degenerate orbitals. In these degenerate orbitals, if you place one electron, they can easily exchange them among themselves. So more is the exchange of electrons, more is the space they occupy. And when electron starts occupying more space, the molecule will be, the atom will become more and more stable. Okay. So since nitrogen offers a lot of exchange energy, which we call as half-filled stability, so it becomes challenging to remove an electron from nitrogen. So while when it comes to oxygen, it is not so much half filled here. So therefore, removing the first electrons is not as challenging as that of nitrogen. But notice, after removing one electron, it has now become half filled and has more exchanges. Therefore, first ionization is difficult for nitrogen, but the second ionization is difficult for oxygen. And the same logic goes throughout the group also. First ionization is difficult for phosphorus, but the second ionization is difficult for sulfur. And the next group elements also arsenic and selenium and arsenic and selenium. Okay. Putting all these things together, now I can say if you go the trend of ionization, if you notice the trend of ionization as it goes from left to right, the ionization is expected to increase because Z effective is increasing. Z effective increases. That is, effective nuclear charge is increasing. So ionization energy must increase. But somewhere in between, there are few exceptions, like nitrogen is supposed to be less than oxygen, but for the first ionization, nitrogen is better. Same goes with beryllium and boron. Down the group, you will hardly see much changes in the trend, except few other groups, like ionization of gallium and aluminium. Then, when it comes to D block, so this is from D block series. D block series, you would notice that hafnium and zirconium belongs to same block, same group, but hafnium has more than zirconium. Okay. In fact, if you notice that this is a period, third period elements. Okay. Sorry, third group elements. So third group elements. The third group elements include, right? The third group elements include scandium, okay, yttrium, lanthanum. Okay. Elements include fourth group elements include titanium, zirconium, and hafnium. Now, when it comes to ionization in the third group, you don't see much problem. Scandium is more than yttrium is more than lanthanum. Down the group, we are expecting to decrease, and that is what will happen. But when it comes to fourth group, the first ionization, if you notice, it is titanium greater than hafnium greater than zirconium. Okay, got it? This is an exception here, and this follows throughout the series of elements. That is, if you notice, titanium belongs to third period, which we call it as 3D series. This is 4D series and 5D series. So between 4D and 5D, there is hardly any difference in the ionization. In fact, more often the 5D has more ionization than 4D. Okay. Check. The same goes with mercury and cadmium also. Cadmium, which is 4D group, and mercury, which is 5D group elements. So for 5D series elements. So you can see mercury would have more than cadmium. Now, what are the applications you will notice from ionization? See, when it comes to metallic and non-metallic character, so we'll see metallic is directly proportional to ionization. If the ionization energy is lower for an element, it also indicates the fact that the metallic character might be more. Okay, correct. Similarly, if the ionization is lower, we can also say the metallic reactivity might also be more. For example, if at all I ask you, what happens to the metallic character of, okay, group 1 elements. So then we say that lithium has relatively less metallic character than potassium, rubidium, and cesium. That also comes with the fact that The reactivity also depends on the same thing. So cesium is more reactive than rubidium, potassium, sodium, and so on. Why is that? Because of low ionization energy. It requires very less amount of energy for these elements to lose out an electron. So therefore, they will be extremely reactive metals. Next thing, stability of the oxidation state. That is, if difference in two successive ionization is observed to be greater than 16 electron volts, then the lower oxidation state is more stable. For example, sodium, if it has to become Na plus, the amount of energy required is 5.14 electron volts. But Na plus to convert into Na double plus, we require 47.2. So the difference is almost 42 units, which suggests that the removing second electron is a very, very challenging role for Na plus. Therefore, if it comes to stability, Na plus will definitely be more stable than Na2 plus. Got it? Second, if the difference is less than 11 electron volts, the higher oxidation state is always going to be more stable. For example, magnesium will require 7.65 electron volts. Magnesium 2 plus requires 15, but the difference is not very high. Hence, the higher oxidation state will be more stable. In the case of aluminium, the values are this 28.45 electron volts, 5.99, 18.83, which suggests that the aluminium plus 3 is more stable than Al plus 3. Clear? So I think up to this point, I hope you guys got an idea. Okay. Now, just to keep a reference of all the ions which we just discussed, let me quickly put those pointers here. So first, lithium is less than boron, less than beryllium, less than carbon, less than oxygen, less than nitrogen, less than fluorine, less than neon. This is left to right for IE1, ionization 1. Okay. Now, when it comes to second group 13 here, you will see boron greater than thallium greater than gallium greater than or equal to aluminum is greater than indium. This will be the important order because that is the only one which violates here. Group 13 violates. Group 14 to a small bit, that is carbon greater than silicon greater than germanium greater than lead greater than tin. So the variation is here, everybody. In the first case, you will see the variation in these three cases. In fact, I'll put it this way. Uh, the entire aluminum is supposed to be here, thallium is supposed to be end. So these two are actually the ones which are violating the form. Now, in this case, lead and tin, both of them are violating because lead is supposed to come before, tin is supposed to come before, then lead. But this is what is happening. Okay, just a second. Right, check. Next, if it comes to group 18, okay, helium is greater than neon, helium is greater than neon, greater than argon, greater than krypton, greater than xenon, greater than radon. Okay, these are few exceptional ones which you need to remember in a group wise. Okay, now let's see the applications, other applications, continued applications of ionization. First, metallic or electropositive nature. I just told you that down the group metallic character increases, right, as the ionization decreases. Reactivity also, if ionization 1 is far greater than ionization 2, then they are highly reactive. That means the gap should be higher. Just like in sodium, we notice that there is almost 47 electron volts unit of difference. So that makes the gap is very high. So we can say that it is more reactive. Ionization 1 is very high, then the reactivity is lower, which is what happens in inert gas cases. Next point is about reducing power. How do we notice the reducing power? See, similar trend has been observed in electropositive character. That is, if it comes to EP, electropositive character, I can say cesium, because it has a low ionization, has a more electropositive character as compared to rubidium, as compared to potassium and sodium, so on. Likewise, barium will have greater than strontium, than calcium or magnesium. Okay, these are more electropositive cases. This is the trend of electropositive nature. Okay. So left to right, what would happen? Left to right, okay, reducing power decreases. Reducing power decreases. For instance, if you compare sodium, that is Na and magnesium, if it comes to ionization 1, okay, correct. So the first ionization between these two, ionization 1 is greater for this. For in the second case, ionization 2 is greater for this one. Okay. Okay. IE1 and IE2 here. We learned this already, that this one is greater and IE2 is lesser, and sorry, it's IE1. IE2 is greater for oxygen. So here I can say that the reducing power is always decided based on first ionization. Okay, inversely proportional to first ionization. So if the reducing power is more, that means first ionization value is less. Okay. So if I compare the reducing power of sodium and magnesium, so sodium is more than magnesium. Clear? So it is directly related to ionization. Right. Now let's get into the third factor which influences the periodic properties, that includes electron affinity. What does that mean? It's quite reverse of what we done for ionization. This is the amount of energy that is released when an atom or when an electron is added to the valence shell, the last shell of an isolated gaseous state atom. Like this, if I take an electron, add it to a gaseous state atom, it will become an ion. Then the energy is expected to release. The released energy is called as electron affinity. By definition, electron affinity is already used as a released energy, so it is positive. But when you write in thermodynamics, right? In thermodynamics, we do not use the word energy, rather we use the word enthalpy. Okay. And as per thermodynamic convention, any energy that is released is always called as exothermic. And in any reaction or any change in state or any change in a species, if energy is required, we call it as endothermic. While in electron affinity, we are expecting that energy should be released, correct? So then, as per convention, it should be exothermic, and exothermic in thermodynamics is always taken as negative sign. Exothermic, the released energy is always expected as negative. Endothermic, which is required energy, delta H is expected to be positive. And that is the same convention we are using here now. So check. If we write that term instead of electron affinity, if I write the term as electron gain enthalpy. So a species is gaining an electron, that's why it is called electron gain enthalpy. It is the same part as a electron affinity, but it is minus of electron affinity value, because electron affinity we are assuming it like positive value, so electron gain enthalpy is a negative value. Okay, so if you are getting a negative value of electron gain enthalpy, that means energy is reduced. Okay, now second thing is the first ion is first electron affinity, that is removing adding the first electron, we are expecting in most cases energy is released. But one thing we can make sure of, that when you add the second electron, right, since this species has already got negative charge, it will never allow another negative charge species to come closer, because there will be repulsions. There will be stronger repulsions. So, in this case, no matter how much you try to add the electron, energy overall is never released. Here, energy is always required. So, I can say that second electron affinity is always negative for an element, which means what is this process? This is an endothermic process now. This is endothermic. Got it? So, adding an electron affinity is negative, which means electron gain enthalpy is positive. Electron gain enthalpy is positive. Okay, let me show you with an example, that is how the successive electron affinity works. For instance, if we have x plus 1 electron, right, it is becoming x minus the electron affinity 1 if it is greater than or less than or equal to 0. The second case, irrespective of whatever it is, as long as it is x minus, and now you are adding to make it as x2 minus, then electron affinity part is always going to be greater than 0. And what is the other interesting part here is that delta, that delta H of electron gain enthalpy can also be less than or greater than equal to 0. But here, electron gain enthalpy, the second electron gain enthalpy will always be negative. Sorry, will always be positive. I wrote this wrong here. It should always be negative. Electron gain enthalpy is electron affinity is negative, so electron gain enthalpy is always positive. Now see the interesting fact that delta H of electron gain total, which is equal to delta H electron gain 1 plus delta H electron gain 2. This is always coming out to be positive. What I'm trying to say is that in all cases of the elements, the second electron gain enthalpy magnitude will always be greater than the first electron gain enthalpy magnitude. So a lot of time questions will be dealing in this aspect, that there are four elements given. You know that some element is given as O minus, some is given as O, something is given as O plus or sulfur plus. If you have to compare them, you need to check out what happens with the second ionization, because second electron gain enthalpy, because that value is very high, overall value will always be positive. Okay, so for example, if I give you reaction like this, O gas is giving out O and adding two electrons to it, it is becoming O2 minus. Then overall, delta H overall has to be greater than 0. And this is a fact for every element. That means if you even take sulfur and if I add two electrons here, it will become S2 minus gas, and delta H overall reaction is always greater than 0. Okay. To be precise, if I take this example of oxygen, adding one electron to oxygen, if it becomes O minus gas, and delta H of electron gain enthalpy, if you have checked out the value, it is 141 kilojoules per mole. Now that you have to mug up, I'm just giving you for reference. So O minus gas plus one more electron become O2 minus gas. delta H of electron gain enthalpy 2 is found out to be 744 kilojoules per mole. So it is pretty much clear that the delta H overall value, right, is sum of these two, which is 744 minus 144, which is greater than 0. Okay. I hope you guys understood what is the successive electron affinity. If there is any problem, you can ask me now. Please check quickly. See. Next. In case if you have an element X, you're adding an electron to it, and that makes it into X minus gas. And this is delta H of electron gain enthalpy 1. And if you talk about X minus, trying to release the electron out of it, correct? It is trying to release the electron out of it and converting into this. Then we call this as, this is ionization energy of X minus. This is electron gain enthalpy of X, correct? By magnitude, because if you notice, these two reactions are just the reverse of it. So by magnitude, these two values are same. Okay, by magnitude, these two values are same. That is, electron gain enthalpy of X is same as ionization of X minus. Ionization of X minus. I guess this is clear. Now let's see quickly what are the factors that affect here. Just like the trends of ionization, a very similar trends are noticed even in the case of uh, electron gain enthalpy. Check. Larger the size, less is the electrostatic attraction. Hence, smaller is the attraction value. So EA value will be lesser. So electron affinity is inversely proportional to size. Okay. Same is the case with effective nuclear charge. If the effective nuclear charge is more, then electron affinity will be more. Because Z effective is inversely proportional to size, I can say electron affinity is now directly proportional to Z effective. And screening factor is also very similar case. Electron affinity will be inversely proportional to sigma. Okay. Half-filled nature. See, for example, nitrogen. We just discussed the fact that nitrogen has degenerate orbitals in 2p and they are relatively stable. Would they like to engage with one more electron here? Answer is no. I mean, normally an atom will immediately accept an electron and release the energy, but not in the case of nitrogen. Nitrogen would be reluctant to accept any electron because it would destabilize its half-filled nature. Therefore, instead of releasing energy, in case if you forcefully feed that electron, the energy is actually required. So I can say electron affinity is negative, electron gain enthalpy is positive. Okay, first electron affinity. And same goes with zinc also. Zinc is 4s2 3d10. It's kind of full electrons. So 4p would be highly reluctant to take any electron into it. So here also EA value is very less. Delta H electron gain enthalpy is lesser but very close to zero. All right. While if it comes to beryllium, beryllium will be also very reluctant to take an electron because 1s2, 2s2 has been already filled. 2p will not be ready to accept an electron into it. Correct. So therefore, electron gain enthalpy is negative, which makes electron affinity is negative, which makes electron gain enthalpy as positive. But once you get one electron in 2p, adding the second electron is not a challenge. In this case, electron gain enthalpy, electron affinity is greater than 0, and electron gain enthalpy is less than 0. And lastly, all the inert gases are extremely reluctant in accepting electrons because their octet is completed. They are very stable atoms. They would not be ready to accept any electrons into it. Got it? Now, here is an interesting fact that we must learn for solving questions. That is, uh, the elements which have negative elements which have negative electron affinity, okay, includes beryllium, magnesium, nitrogen, helium, argon, neon, krypton, xenon, and radon. So out of which, except the first three, rest all are inert gases only. Rest all are inert gases only. Okay. Important list, students. Important list here. So you should know that which are the elements which will give negative electron affinity or positive uh, or positive delta H electron gain enthalpy. Done. Right. Now notice this one. If you go from left to right in the periodic table, left to right, electron affinity variations if you notice, first, lithium is less than boron, is less than carbon, is less than oxygen, is less than fluorine. Correct? Less than fluorine. Which of them we have eliminated here? Beryllium, nitrogen, and neon. Why did we not include them? Because these will have electron affinity negative or delta H electron gain enthalpy positive value. This is from left to right. If you go down the group now, check out down the group. In the case of going down the group, first group 1, we have no variation. Lithium is greater than sodium, potassium, rubidium, cesium. And group 2, right? Group 2, we have calcium, strontium, barium, okay, radium, uh, radium, magnesium, and beryllium. Got it? Now the order is slightly different here. Correct? You can see order is slightly different here in the case of calcium, in the case of group 2. Why is that different here? See, magnesium and beryllium, we just discussed that they would have actually what value, right? Because they belong to this category where they do not take electrons and release energy. Since they do not release energy, so we will not be including those two here. So we only need to compare calcium, strontium, barium, radium. And that, they will regularly decrease down the group. Next one, if you compare group 3 here, which means group 13. Group 3 and group 13 are same. So here, aluminium is greater than boron, is greater than gallium, is greater than thallium, is greater than indium. Okay. So in comparison to aluminium and boron, see, boron is still little reluctant, but aluminium will easily take up the electron. So after aluminium, we come across boron, gallium, thallium, indium. Okay. Next is group 14 or 4A. So in case of group 4A, silicon is greater than carbon, right? Is greater than germanium, lead, and tin. So variation is observed here in tin case and these two cases. Clear? Now, why this thing is happening here when it comes to group 13 to 17, right? If you notice the electron affinity here, so why this change is happening, let us understand that. Once again. Okay, now notice. So there is a certain variation between aluminum and there is a certain variation in here with silicon. Now, same logic applies even when it comes to group 16 also. In group 16 also, which is 6A, correct? In group 16 also, you will observe that sulfur is greater than, selenium is greater than, tellurium is greater than oxygen. Now, this is even worse. That is, oxygen has come to the end now. And lastly, if group 17 is concerned, which is 7A, here you would notice that chlorine is greater than fluorine, then bromine, then iodine. So why this variation between chlorine and bromine came across? So let us understand this logic here. See, what is happening here is when it comes to second period elements. Second period elements include uh, boron, right? Boron and carbon, nitrogen, oxygen, fluorine. Now these are small size atoms. Since they are small size atoms, for example, if you have something like, fluorine, fluorine in the first orbit will have two electrons. In the second orbit, it is supposed to have seven electrons. Three, four, five, six, seven. So we have seven electrons. Sorry. So check. So if at all I add one electron here, correct, to this orbit, so what would happen? As soon as we get one electron here, then because you're adding the electron to the same orbit, the closeness between the electrons increases here. Okay, except for this nucleus here, except for this nucleus, the closeness between the electrons increases. So that gives you something called internal electron repulsions. So intra electronic repulsions. Although energy is released, although energy is released here, it also needs to account for certain intra-electronic repulsions. And these intra-electronic repulsions would be relatively higher in second period elements because they are smaller sized atoms. After this intra-electronic repulsions can be ignored because the idea that the electrons are close to each other, that will not account so much as you go down the group here. So therefore, this factor, intra-electronic repulsions or electron-electron repulsions, is more significant, more significant in second period elements. That's the reason why boron towards fluorine, if you compare them with their next respective elements in their group, the next element groups will always have better value, right? Better electron affinity than this group 2 elements. Okay, so that's what is happening in all these cases. See why aluminum is greater than boron. Same way, why silicon is greater than carbon, why sulfur is greater than oxygen. See, oxygen is so much weaker that now it is even lesser than selenium and tellurium. And why chlorine is greater than fluorine here. So all these four are explained on the basis of uh, intra-electronic repulsions. Now, listen one, between sulfur and oxygen there is a huge gap, but you might expect the same thing between chlorine and fluorine also. But in the case of oxygen, even after adding an electron, there is no extra stability that you are getting. We are not gaining any extra stability here. But when it comes to fluorine, right? Fluorine taking one electron, it will complete its octet value. And because it gets an octet completion, huge amount of energy is released. Okay. So fluorine, although it holds on to high electronic repulsions, it is also releasing large amount of energy because it is completing its octet. That's the reason you will not see lot of variation between chlorine and fluorine, but a very high variation between sulfur and oxygen. Okay. Now, general comparison, if you notice, between nitrogen, phosphorus, oxygen, and sulfur, sulfur would have more, then oxygen, then phosphorus, then nitrogen. Of course, when it comes to nitrogen and phosphorus, they do not have a positive value at all. Electron affinity values are not positive here. Okay. Few more cases, what you need to learn here, right? What are the other cases that we need to learn here? Check out here. Uh, when it comes to group 15, okay, it is uh, bismuth, sorry, it is bismuth which will release more energy than antimony, arsenic, phosphorus, and nitrogen. Okay, and then when it comes to uh, group 16 here, I mean, sorry, group 18 here, if you compare the last one, group 18, generally electron affinity of all group 18 are assumed to be zero. So they are not exactly zero, but when you use that word in terms of electron affinity, we always use it as zero. But if it comes to electron gain enthalpy, okay, when it comes to electron gain enthalpy, then you will have a certain order in this case. Correct? That is delta H of electron gain enthalpy of group 18. So that includes first one, neon, which has the highest value, correct? And then argon and krypton, almost argon and krypton have same value here, correct? And then comes xenon, then comes xenon, and then radon, and last comes helium. Have you noticed something? This is all I'm talking about positive value. I'll give you the values also. This is 116 positive value. Argon and krypton positive 96. Xenon positive 77. Radon positive 68. And helium positive 48. Correct? These are all in kilojoules per mole. Correct? So what did you notice from here? Higher the value, that means it has the high resistance towards electron accepting nature. So it will hardly going to attract any electron. In fact, none of them will attract the electrons here. But given the chance, if they have to take the electrons by accepting, I mean by taking some energy, then neon has to take how much amount of energy? It has to take close to 116 kilojoules per mole of energy. Okay. So these two are another important cases we need to know. Any doubt from electron affinity, everybody? Please check. Let me know. Let's go to the next important term, which is electronegativity. Okay. See, The tendency of an electron to pull the share pair of electrons in a covalent bond is generally termed as electron negativity. Okay. Expectation is that we should have a polar bonds here. Correct? We must have polar bonds. What polar bonds? Polar covalent bonds. That means if you have a bond between A and B here, correct? You have two conditions. If electronegativity of B is greater than electronegativity of A, then the bonded electrons between A and B, correct, would be more close to B. That that gives that makes them to achieve some polarity on this. So the polarity is developed because of this electronegativity. Correct. Same way, if electronegativity of B is less than electronegativity of A, then between A to B, if you compare, then A would have more electrons here, delta negative, delta positive, and polarity here is developed again. So it all depends upon the electronegative difference. So this is some kind of a power to pull the bonded electrons. Which bonded electrons? Sigma bonded electrons. What are sigma? What are pi? We will learn going ahead. But as of now, remember a single bonded electrons which you have, that strength, that how strongly they can pull it. Okay. These are polar covalent bonds. What are non-polar covalent bonds? Non-polar covalent bonds. Non-polar covalent bonds are the cases where the electronegative difference is zero, or electronegative difference in the above case was greater than zero. Here it is less than zero. That means a bond between chlorine and chlorine, hydrogen and hydrogen, oxygen and oxygen, nitrogen and not nitrogen. All of these are non-polar covalent bonds. Correct? Now, let me quickly give you a glimpse of what is the difference between electronegativity and affinity. First of all, we write electronegativity with respect to an atom in which a molecule with a covalent bond is present. So we can only discuss the electronegativity when there is a molecule present. So it is a relative term. So remember, it is a relative term. While when it comes to electron affinity, we write that with respect to an atom, and that too in an isolated gaseous state atom. This is not an energy term, rather it is a reference in terms of powers or relative powers. This is an energetic term. That means it is a absolute energy value, that how much is released or how much is gained. Here, this increases in the period. Okay, that means left to right it increases, correct? But electron affinity had an irregular trend. We saw that group 15 had a difficult trend, and uh, 2 group 2 beryllium and magnesium did not even offer the electron affinity. Last group 18 does not have a great trend. So you can see this has an irregular trends. While electronegativity has a very regular trend. Since it's a relative term, you will not find any units for it, while electron affinity is measured in terms of electron volts per atom or kilojoules per atom. So this is a relative term, this is an absolute term. So this is the basic differences which you'll identify between electronegativity and electron affinity. Now, electronegativity was defined on basis of multiple scales. Since it's a relative form, it has been explained on multiple scales. In this scale, he took the reference of fluorine. So fluorine was taken as a reference, and that has the highest value. As you will not find any bond of fluorine where fluorine is actually pushing the electrons away. Rather, the electrons are always pulled towards fluorine. So in a way, fluorine is a boss of electronegativity. It will always be accepting the pair of electrons towards itself. So that was given the highest value as 4. Why 4, sir? So that the other elements can be identified easily with simple numbers. So based on Linus Pauling's calculations, After fluorine, he noticed that there is a certain trend that is followed. When he calculated for oxygen, it was 3.5. For nitrogen, it was 3. For carbon, it is 2.5. Boron, it is 2, 1.5, and 1. A very, very regular trend of increasing order. And when it comes to sodium towards chlorine, a trend very close to that is also followed. Chlorine, on the other hand, is slightly greater than nitrogen. Okay. And then you have bromine and iodine together here. If you put all of them together, this is the order that you will identify. So fluorine, oxygen, chlorine, nitrogen, boron, sulfur, iodine, carbon will be almost same. But when you make the reactions, guys, then give preference most to sulfur, then iodine, then to carbon. And carbon is greater than phosphorus, then hydrogen. After hydrogen, rest of the parts which you have, this one and this one, you can see these are all those metal forms. So generally notice all the metals will have lesser value than hydrogen. So hydrogen is like a borderline case which separates the non-metals towards metals, non-metals and metals. Okay. Now, what are all the different scales that are being used to measure the electronegativity? So one scale, that is old scale, that was used was Mulliken scale. Okay. So Mulliken scale. The Mulliken scale was like in taking average of ionization of that particular element and electron affinity of that particular element, both positive values, correct? And that divided by 2. It should be represented in electron volts per atom. Okay. And when we notice the values of Mulliken scale, one trend has been identified that all the electron negativity which we identified in Pauling scale, they were 2.8 times lower than that of Mulliken value. Got it? So this is a trend that has been observed between Mulliken scale and Pauling scale. Okay. Mulliken scale, clear? Sorry. So Pauling scale, if at all I write the same value in terms of Pauling scale, I can write this as IE1 plus EA1 divided by 5.6 in electron volt per atom. If you write in terms of uh, if you write in terms of uh, units for electron negativity, then this is the way you can represent. Next, you can also write this in terms of Pauling scale as ionization energy 1 plus electron affinity 1 upon, it is about converting this electron volts per atom to kilocalories per mole. In that case, it will become 2 times of 64.5, and that will convert into kilocalories per mole. Okay. Nothing to prove here. We just need to remember the equation. This is hardly asked. Only these two are being usually asked in exams. So remember what is Mulliken scale, what is Pauling scale, and how they are related with each other. Okay. Another scale which is used is Alfred Rachow's scale. Alfred Rachow's scale. Okay. That is XAR, Alfred Rachov scale, is Z effective into E square. E is the electron charge by R square minus 0.359 Z effective divided by R square. Correct. So here Z effective you can calculate using Slater rules, that is Z minus sigma. This we have done it, and use that Z effective, substitute that values here, you will be able to get uh, X of AR value here. And this value, when you compare that with the Pauling scale, was found to be AR plus 0.744. Okay. This is another important relation between Pauling scale and Alfred-Rochow scale. Got it? Now see, when it comes to units, you should always take the R units in Armstrong. While calculating here, we should always take them in Armstrong units. All right. These are the scales of electronegativity that might be used. Again, Rochow scale is not directly used as a formula, guys, but you need to remember this part. That is, if Alfred Rochow's value is already given, then you just have to add 0.744 and this will come. Okay. See, since this wording has been mentioned in NCERT, that's why we should be using the formulas. Okay. Otherwise, not direct formulas, formula-based calculations are asked. Just the relationship-based calculations, that is Pauling's to Alfred ratio or Pauling's to Mulliken, will be asked. Now, let's go through applications of electronegativity one by one. First one is a bond strength. Okay. Now, if the electronegativity, this is X here, that means electronegativity difference. If that electronegative difference increases, more and more electrostatic attractions would happen and the bond will become stronger. Bond will become stronger. So, when it comes to bond energy of HF versus HCl versus HBr versus HI. If you notice the electronegative difference, guys, this is 4 minus 2.1, correct? So this is 3.15 minus 2.1. This is 2.8 minus 2.1. And this is 2.5 minus 2.1. So you can see the electronegative difference is decreasing. Since electronegative difference decreases, the delta positive, delta negative magnitude will decrease. Hence, if it comes to electronegative bond energy, this is the order that we need to follow. This is the bond energy order. Okay. Similarly, if it comes to bond energy, you are comparing that with a C double bond C versus a C double bond N, okay, versus a C double bond O. Let us say this is X, Y, and Z energy that we need to compare. Now, notice that electronegative difference here, delta positive, delta minus, delta positive, delta minus. Here, there is no polarity at all. So, you can see again, electronegative difference is increasing. So, I can say the bond energy between Z will be for Z greater than Y greater than X. This will be the case for bond energy. Okay. Next one is, sorry, next point is more the percentage S character, more percentage S character, okay, stronger the bond energy as electronegativity increases. Okay, what does this mean? Check. If I'm talking about C triple bond C and H, if you may not know the hybridization, don't worry about it. Here the carbon is expected to have sp hybridization. What is that? I'll explain you as we discuss the chemical bond. Suppose if there is, if there is a double bond here and we have C H bond like this. Now, in this case, the hybridization is sp2. Correct? In this case, hybridization is sp2. And last case, here, if the hybridization is sp3, here hybridization is sp3. Correct? So percentage S is calculated based on number of bonds here. So S, and I'll write down here S, SP, SP2, SP3. This is the case you have. So percentage S character, if you notice, this is 100%. There is only one S orbital. So it is pure. Second one is 1 out of 2. So that makes it 50%. Third one, 1 out of 3. So that makes it 33.3 percentage. 1 out of 4, that makes it 25 percentage. So that means as the number of p orbitals increases, the percentage S character decreases. And percentage S character decreasing will always influence the electronegative nature also. That means a carbon electronegativity here, let's say the electronegativity here, let us call this as X. Electronegativity of this carbon, let us call it as Y. Electronegativity value of this carbon is Z. So what you would notice that electronegativity value of this carbon X is greater than Y greater than Z. So that means percentage S character is more, which is directly impacting electronegativity of an atom. And that will always be more if the percentage S character is more. Okay. As of now, keep that in mind. What is percentage S character and how it is varying? Going ahead, we'll be able to learn, how exactly to figure out what is hybridization and how do we relate that with electronegativity. Next, notice this one. If you have to check out mathematically, what is the bond length between AB, which is polarized atom or two different electronegative atoms, that can be calculated using Stephenson's Shoemaker formula. I used this terminology before, if you remember. That is, if we have DAB, it will be RA plus RB minus 0.09 into electronegative differences, XA minus XB. Okay. Okay. This is like this. If you have bonding between two atoms, correct, and center to center, this distance is bond distance here, D of AB. If this is pure radius of A and this is the pure radius of B, then this plus this minus of this entire thing, that would be D of AB. Okay. Please check out the question here and try to solve it, everybody. Just use the formula and try to figure out the bond length between H and F. I'll give you 2 minutes. Try it out. Any answers? No? Nobody got the answer? Okay. Let me put and check. R of F and F will be half of the bond length of F2. So which is 1.44 by 2, which is 0.72. R of hydrogen will be bond length by 2, which is 0.74 by 2. Okay, this is 0.37. And now I just need to put those values here. So D of HF will be equal to 0.72 plus 0.37 minus 0.09 into electronegativity of fluorine is 4, hydrogen is 2.1. So I'm getting this as 0.72 plus 0.37 minus 0.09 into 1.9. Solving it, I'm getting it as 0.919 Armstrong. Okay. Now, if you simply add the values of RF and RF plus RH, if you add that, how much we are getting here? So you are getting this as 1.09 Armstrong. So you can clearly notice that RF plus RH overall is greater than D of HF. Okay. So which clearly suggests that whenever there is an electronegative difference, the bond length decreases. Okay. See, the next application of electronegativity is to check on the charge of the ions. If more and more negative charge is accumulated, electronegativity will decrease because it already has an electrons. It will has no purpose to again pull the electrons. And more positive charges develop, it will have higher purpose to always pull the electrons or pull the sigma electrons to come closer to it and try to nullify the charge. Okay, that's why negative charge decreases, electronegativity increases. Positive charge increases, electronegativity increases. So this is the electronegativity order for all of them. Okay. This electronegativity can also be, this kind of charges can also be observed in something called oxidation states. Oxidation states. So oxidation state is like a hypothetical form where we can say higher the oxidation state, higher the oxidation state, then higher the electronegativity. Okay. And if you notice MnO, Mn2O3, MnO2, Mn2O7. If you compare the electronegativity, correct, this would be more. How do we calculate the oxidation state? See, certain elements have some permanent oxidation values like oxygen. Oxygen always pull electrons from metals and it will always acquire -2 charge. So in this case, I can write it as X minus 2 equal to 0. So X is the oxidation state of manganese. Here, 2X minus 3X equal to 0. 3 into 2 equal to 0. So X is equal to 6. X is equal to 3. Here, X minus 4 equal to 0. So X is equal to 4. And 2X minus 7 into 2 equal to 0. So X is equal to 7. Okay. This is how you identify the oxidation states. So if higher oxidation state is present, that means the metal at the center, I'm talking about the manganese, that will have more electronegative nature. So I'm talking about electronegativity of manganese. Yeah. Let me show another example. Suppose if you have PH3, PCl3, and PCl5. Here, phosphorus has -3 oxidation state because hydrogen is supposed to be +1 form here. So X is equal to -3. And here X plus 3 into -1 equal to 0 because chlorine are always expected to show -1 state. And X plus 5 into -1 equal to 0. So X is equal to -5. Sorry, +5. So oxidation state here is +5, +3, -3. +3 and +5. So highest oxidation state, again, you'll notice it for PCl5. So electronegativity of phosphorus. Okay. Done. Next. In case the oxidation state is same, if oxidation state is same, Then check electronegativity of side atoms. Okay, higher electronegativity of side atoms, more electronegativity of central atom. Okay, so therefore, if we check out, we have PF3, PCl3, PBr3, and Pi3. Okay, now you can see electronegativity wise, we know that fluorine is greater than chlorine, is greater than bromine, is greater than iodine. Since fluorine is more electronegative, that also makes this phosphorus to become more electronegative. So in this case, if we say the phosphorus here is X, phosphorus here is Y, phosphorus here is Z, and phosphorus here is some Q, then electronegativity of the phosphorus in all these four would also have a variation. That is, X will have more electronegativity than Y, then Z, then Q. All right. So electronegativity of the element is subject to change. I mean, it's subject to the atoms connected to it. Okay. Is this point clear, everybody? Check out how the charge and oxidation state varies the electronegativity. Next thing, I told you about hybridization already. Okay, wait, I'll give you two more examples for that. Suppose if you have HOCl, HClO2, HClO3, HClO4. Oxidation state of chlorine here is +1, +3, +5, and +7. So if I compare this and also let's say HCl, in HCl oxidation state is -1. So if this is X, Y, Z, P, Q, then electronegativity of chlorine, if you compare in these cases, then definitely P is greater than Z, then Y, then X, and the least will be Q. Okay, so this is how the electronegativity varies. Next, if we have CF4, then CCl4, CBr4, and CI4. I think just by watching it, you should be able to say it now. So electronegativity of the central atom here, in this case is carbon, it will have a variation. So therefore, CF4 will be greater, and this is the order that is followed. Check quickly. And everybody, please check. Next, if it comes to hybridization, correct. Of course, we have not discussed anything about hybridization, but I told you like just check out the percentage S character. So percentage S character, if that character is more, then the electronegativity of that particular atom is more. So if a carbon with sp3 is present, a carbon with sp2 is present, a carbon with sp is present, then electronegativity of this would be greater. Okay. Another example, I'll just show you the example. CH3NH2, like this. CH3, CH double bond N and H. CH3, C triple bond N. Now notice this nitrogen does not have any pi bonds. I mean, double bond, if you have written, that is called pi bond. Since I only wrote single bonds around it, that means it has zero pi bonds. Here it has one pi bond. Here it has two pi bonds. See, more number of pi bonds relates to more percentage S character always. And the hybridization of nitrogen here, going ahead, we learn how to calculate the hybridization also. In this case, nitrogen is sp3. In this case, nitrogen is sp2. And in this case, nitrogen is sp. So that makes this particular nitrogen here, here, and here, if you compare. So again, I can say the same thing. Nitrogen with sp2, sp3 will be lesser electronegative than sp2, then nitrogen with sp. So this is the electronegativity. This is how it varies. Okay, please check quickly. Then see, next one is ionization and electron affinity. Okay, how is this variation observed? If ionization energy increases, electronegativity, electropositivity decreases and electronegativity increases. That is, if you compare the ionization of lithium is greater than sodium, potassium, rubidium, and cesium. While now if you compare the electronegativity, the same order will be followed. Okay. So electronegativity of lithium is greater. Likewise, if I compare the electron affinity also, if that is greater and electronegativity will also be greater in general, of course, it is not followed in all the cases, but in general, this is how it varies. Okay. Implies, if you notice this example, okay, fluorine is greater than chlorine, greater than bromine, greater than iodine. Of course, there is slight variation here, you know that. But generally, electron affinity increases means electronegativity increases. Okay, clear? So therefore, we can say higher the ionization value and electron affinity, greater is the electronegativity value, and which can clearly you can relate that with the electronegativity of an element which is measured from Millikan scale. Electronegativity which is measured from Millikan scale, which is ionization energy plus electron affinity energy divided by 2. By the way, when I'm taking electron affinity here, I'm considering it as a positive value. Okay, I'm not considering as a negative value. Clear? Done. Next, notice what are all the exceptions here in case of electronegativity. Exceptions in trends of electronegativity. Group 13 is one exception where boron is greater than thallium, is greater than indium, is greater than gallium, greater than aluminium. Aluminium has the least. Okay, next. Group 14. Group 14, carbon is greater than silicon. Then germanium and tin almost will maintain the similar electronegative nature compared to lead. Sorry, compared to lead, which is slightly more. I'll give the exact values also. 2.5. All of them together is 1.8. This is 1.9. Next, group 15. Group 15, nitrogen is greater than phosphorus, greater than arsenic. Antimony, bismuth would be almost the same. It is 3, 2.1, 2.0, and 1.9. So when it comes to group 16, oxygen greater than sulfur, selenium, tellurium, and polonium. So this is 3.5 going towards 2.5, 2.4, 2.1, 2.0. Then group 17, if you notice, fluorine, chlorine, bromine, iodine, astatine. This is a regular trend in case of group 17. Okay. Okay, I'll just write down no exception. No exception. That's it. This is the trends which you need to know it from electronegativity. Clear? Everything is done. Here, everybody. The last thing we'll study today is about acidic and basic strengths. Okay, in the case of acidic and basic strengths, what do we notice? First, you check out the nature of hydrides. Okay, so hydrides as in the elements which are directly connected with hydrogen. So if you notice from left to right, we have uh, acidic strength is directly related to electronegative difference. Okay, that is, if you compare methane, which is from group 14, ammonia from group 15, water from group 16, and HF from group 17, we can say that the acidic nature of HF is greater than this because electronegative difference is increasing. Okay. So acidic strength would be varying this way. And this logic follows even in the case of the next group elements, silicon, phosphorus, sulfide, and chloride. Here also, acidic strength varies this way. Got it? So these two are acidic strengths. While going down the group, check out down the group here. So if you go down the group here, you will notice that, acidic strength only depends. In fact, it depends on electronegativity, but mainly depends upon lesser bond dissociation energy. That means bond strength. Weaker the bond, more is the acidic strength. So therefore, if we compare HF, we learned already HF, because of more electronegative difference, it has stronger bond. So because it has stronger bond, it is difficult to break compared to HCl, compared to HBr, compared to HI. So this is the acidic strength. The same follows for the other group also. For example, H2O is weaker acid than H2S, is weaker acid than H2SE, is weaker acid than H2TE. This is the acidic strength. Okay. Same goes with ammonia also. If you notice, ammonia lesser than PH3, lesser than ASH3, lesser than SPH3. Okay. These are all from the groups here. Done? Right, guys. Okay.